Now let's take a look at some other features of the Aviatrix platform. Site to cloud and other services to connect to external networks. When enterprises build applications in the public cloud, the consumers of those applications tend not to be in the cloud. They tend to be in on-prem data centers, such as branches, customers, or partners. They need to have secure hybrid connectivity from on-prem to resources in the public cloud, whether that's using encryption or using private IPs. The challenge comes with deploying this at scale and having day two operations tools for visibility and troubleshooting. Moreover, it is just about guaranteed that they'll run into an issue of overlapping IP addresses. CSPs will tell you to avoid overlapping IPs. But when you have different business units that pop up as a result of a merger or acquisition, or you have business units doing things on their own, like shadow IT, before needing to connect with the rest of the network, it is inevitable that you will have overlapping IP addresses. Under the multi-cloud network architecture, the consumers we are referring to reside in the cloud access layer. So what's the solution? The solution is Aviatrix Site to Cloud for hybrid connectivity. Site to Cloud will build a connection from the cloud to on-prem. It could be a data center, branch, partner, SD-WAN, or even cloud-native constructs in a different administrative domain. You can also use it to connect to smart IoT devices or satellite or 5G modems. As with all other features on the platform, the Aviatrix controller will automatically configure the tunnels between the gateways and the other end. Based on the requirements and use case, you can select either IPsec or GRE as the tunnel link protocol. Site to Cloud is easy to use and template driven. You can download the config that is applicable for the vendor used at the remote end. And you can use the instrumentation in the platform, such as diagnostics tools and visibility, to overcome challenges such as overlapping IPs. Let's take a closer look at some site to cloud use cases. The first one is where an enterprise wants a backup path for their private circuits, such as Direct Connect, Express Route, Cloud Interconnect, or Fast Connect, using IPsec over the internet. Organizations will continue to use their primary private circuits for hybrid connectivity. And when that primary circuit fails, Aviatrix traffic engineering will automatically switch over to the backup IPsec links. The next use case is shared services multi-tenant architecture. This is used very commonly by SaaS providers, as well as service providers, as well as enterprises who need to have multi-tenancy for internal customers. Customers are accessing shared services as well as specific local resources. A common challenge these customers face is when the IP ranges of multiple customers overlap with each other. Aviatrix solves this challenge by providing complete segmentation to each customer using multi-cloud network segmentation. The third use case is for enterprises with different types of customers, both managed and unmanaged. Managed customers are those who can control hybrid connectivity by deploying Aviatrix gateways. For example, in this topology, customer 3. Unmanaged customers are those who bring their own devices at each site for hybrid connectivity to the cloud. And these devices could be native cloud constructs such as AWS VGW or Azure VNG, or they could be third-party IPsec capable routers. Managed and unmanaged customers could be in any cloud, but they all need access to shared services in the cloud, and they need to access resources in the on-prem data center. The biggest challenge they face is overlapping IP address space. And as you can see in this topology, they all use the 10.10.0.0/16 address space. Often, the enterprise will run out of private IP ranges and cannot provide one-to-one NAT translation. Aviatrix has an elegant solution called Mapped NAT that uses unique subnets called virtual subnets to overcome this conflict. The next topic is routing control. The problem that enterprises face is as follows. Native constructs have no route control mechanism. So in an on-prem environment such as a partner or branch site connects to the cloud, if it inadvertently advertises a route that it shouldn't, the route will incorrectly get installed. In this diagram, you can see partner or branch sites connecting to the cloud and advertising BGP prefixes. And if any of those sites advertises an unwanted prefix by mistake, then there is absolutely nothing you can do. In the worst case scenario, the remote site advertises a 0/0 or quad 0 route. At that point, they will attract the default route of all cloud traffic towards them and will cause a major outage. You end up with a black hole and nobody is happy. You still want connectivity with those partners and learn legitimate routes, but just not unwanted routes. Aviatrix provides an elegant solution for these unwanted prefixes and gives you full control with the BGP route approval feature. Let's take a look at an example. BGP prefixes or routes arrive at an Aviatrix transit gateway in any cloud from a partner site. The connection could be over a private circuit or over the internet. The partner device could be a router, switch, or firewall. The transit gateway informs the Aviatrix controller that it received a new route from this partner site. In turn, the controller will notify the administrator via email. Now it is time for the admin to approve or reject this new prefix. This action can be done via the controller UI or via Terraform. If the admin approves the route, then the route will be installed in all Aviatrix gateways, in all spoke VPCs, VNets, or VCNs. And the feature is very flexible in that you can pre-approve prefixes so that the administrator doesn't always have to be in a reactive mode. SD-WAN integration. SD-WAN was built from the ground up to improve the wide area network. It's meant for remote sites to use multiple WAN circuits effectively to stop using MPLS providers. And it did that really well. But the cloud was, and still is, an afterthought for SD-WAN vendors. They're still struggling to figure out the cloud piece of their architecture. They're not aware of native cloud providers' APIs or multi-account structures or VPC and VNet peering or cloud route tables or subnets in the cloud. SD-WAN vendors might say they're multi-cloud, but they don't talk about the role of transit in the cloud. And because of their limited knowledge of cloud APIs, their solutions are IPsec-based, which, as we just discussed earlier, is limited to 1.25 gigabits per second throughput. Moreover, SD-WAN vendors struggle to figure out advanced routing features like BGP prefix summarization and traffic engineering in the cloud. Additionally, SD-WAN vendors are unable to seamlessly enhance the security posture of enterprises with insertion and orchestration of advanced services like next-gen firewalls, and manual insertion is hard. Aviatrix has various design options to support all popular SD-WAN vendors, such as those shown on the right. BGP over IPsec is a legacy solution with limited throughput of 1.25 gigabits per second because of the known IPsec limitation that we discussed previously. Great for security, not so great for performance. The BGP over LAN solution is a popular option when the risk tolerance is greater and performance beyond 1.25 gigabits per second is desired, or the SD-WAN vendor simply does not support IPsec in the cloud. With this solution, the SD-WAN hub appliance in the cloud is on the same subnet as the Aviatrix gateway. The BGP over GRE option is another way to get past the 1.25 gigabits per second throughput limitation. It's specific to clouds that support the GRE tunneling protocol, which at this time is AWS only. With Aviatrix, SD-WAN traffic from on-prem sites such as data centers and branches can be seamlessly inspected by next-gen firewalls in the cloud transit layer using a feature called FireNet. We'll go over this feature in more detail later in this module. Aviatrix also provides advanced traffic engineering options such as routing control, which we just went over in this module. Finally, all other Aviatrix benefits apply, such as segmentation, as well as enhanced visibility of all your traffic in the cloud from on-prem via SD-WAN. At the end of the day, these are just site-to-cloud connections. As a matter of fact, with site-to-cloud, you really don't need SD-WAN at all. You can just use site-to-cloud tunnels between the cloud and on-prem. And you can extend cloud to on-prem over an Aviatrix fabric using Aviatrix Secure Edge gateways. In this topic, we'll cover the user VPN feature of the platform and discuss how Aviatrix can provide secure user access. Remote users, such as developers and SREs, have a requirement to connect to public cloud resources in a secure and seamless manner. A key requirement for these remote users is to incur lowest latency possible when accessing resources in the cloud. Since the users are remote, they might be traveling, and they could be anywhere in the world, if they are far away from the resource they need to access, then their latency will be higher, and as a result, they will experience degraded performance. Based on their location, they could use different profiles, but that is a very difficult position to be in. In order to make it a seamless experience, the user should not need to worry about managing different profiles and certificates based on their geolocation. Along these lines, legacy approaches such as backhauling VPN traffic to on-prem data centers first must be avoided at all costs. In other words, VPN traffic must not be terminated in on-prem data centers prior to redirecting to the cloud. That would only add latency in the path and is extremely inefficient. When remote users connect to resources in the cloud, security must be enhanced by leveraging enterprise-grade identity provider solutions that support the Security Assertion Markup Language, or SAML protocol. Users must be authenticated by IDPs prior to accessing cloud resources. And finally, since most enterprises have applications in multiple clouds or are planning to do so soon, the solution must have a repeatable architecture for repeatable, secure user access. Now let's take a look at the Aviatrix User VPN solution. As usual, everything stems from the centralized control, management, and automation plane, which is the Aviatrix controller. In this example, we have an AWS environment. Using the MCNA architecture, we have different workloads in their respective application VPCs with spoke gateways. Those spoke gateways are connected to transit gateways in a transit VPC. And we have remote users that fit different security profiles, such as partners, contractors, and employees. The solution is to deploy a dedicated VPN VPC with Aviatrix gateways that will terminate VPN connections from remote users. These are known as VPN gateways. You have the choice to deploy this in a scale-out manner with a regional load balancer of the CSP. In this case, it is the AWS Network Load Balancer, or NLB. But with Azure, it would be an Azure Load Balancer. And with GCP, it would be a Network Load Balancer. The important thing to note is that the Aviatrix controller will take care of automatically spinning up the load balancer and adding VPN gateways to the target group or backend pool. So connections from partners would arrive on the load balancer and terminate to any available VPN gateway en route to the environment it is permitted access to. Likewise for contractors, they will only be able to access workloads in the environment they are allowed access to. When employees try to connect, it's really up to your corporate security policy what they are allowed to access. Typically, they are given more access than partners or contractors. And that's the case in this example. This solution uses the OpenVPN standard, and any OpenVPN client is supported. For enhanced security and compliance reasons, enterprise-grade identity providers, or IDPs, are often required. These are where the directory of users is stored. Aviatrix supports a wide range of IDPs, such as Okta, Duo, Azure Active Directory, and OneLogin. Any IDP that supports the SAML standard is supported. What about if other clouds are brought into the picture, like GCP or Azure? At that point, users can connect to VPN gateways in AWS, GCP, or Azure, and then access the resources by using the Aviatrix multi-cloud transit backbone. What if resources are on-prem? That can be solved through a site-to-cloud connection. Users would terminate their VPN tunnels on an Aviatrix VPN gateway in any cloud and then connect to on-prem via the site-to-cloud connection. Now, since users could be anywhere, in order to meet the requirement of low latency, you can use the GeoVPN feature, which leverages latency-based routing in Amazon Route 53 or similar technologies with other CSP DNS products. Additionally, User Accelerator is a feature in which Aviatrix integrates with AWS Global Accelerator to get the user onto the AWS Global backbone as early as possible in order to achieve not only low latency, but also deterministic latency. In this section, we'll cover firewall inspection best practices in the cloud. We all agree that when it comes to security, The best approach is a layered model that uses defense in depth. For applications that are communicating within the same spoke VPC, VNet, or VCN, the best approach is to utilize layer 4 constructs that come with the CSP, such as security groups, network security groups, or VM firewalls. For ingress or egress traffic flows from the spokes, there are a couple of options. It all depends upon the priority of the application and the requirements of the security team. The first one is when it is a low priority environment. In that case, a combination of layer 4 inspection and egress FQDN filtering might be adequate. The other option is to use a next-generation firewall for layer 7 inspection. Obviously, layer 7 inspection comes at a cost, but here you'd want to take advantage of specialized vendors like Palo Alto Networks, Fortinet, or Checkpoint. What options do you have in the public cloud when it comes to architecting firewalls? Let's take a look at this from the perspective of feature maturity on the vertical axis and ease of use on the horizontal axis. Instance-level firewalls refers to layer 4 firewalls, which are essentially security groups and network security groups applied to VM instances. Depending on the number of applications, you can easily have a sprawl of these security groups and NSGs. They can help you with compliance, but they're not usually sufficient on their own. Recently, CSPs have started productizing layer 7 firewalls. However, they tend to lack deep security intelligence and maturity. They don't provide adequate visibility and troubleshooting tools. And they're difficult to insert in the traffic path because it is a manual process which incurs errors. The next option is to insert next-generation firewalls, such as what you may have been used to in on-prem. These solutions have been around for a long time and have typically established themselves as best of breed in this space. However, they are also very difficult to insert into the traffic path because they are not handling the control plane and are just one component of the data plane. They expect the customer to come up with service chaining solutions, which include route management and traffic steering. The next option is to integrate firewalls into the transit layer. This offers better performance and allows for a policy-based approach. It is an architecture that repeats itself within a region, across regions, and across clouds. Now we'll talk about the Aviatrix integrated firewall solution. Aviatrix gateways have a built-in knob that enables the centralized stateful firewall feature. This is a layer 4 firewall, and it's best suited for small-scale environments where there's no need for a next-gen firewall. You can take advantage of an Aviatrix feature called Single AZ HA, which we'll talk about in a moment. The advantage you get with this feature is that because it is centrally placed in the transit layer, you can control traffic from one spoke VPC, VNet, or VCN to another by providing layer 4 inspection. In addition to inspecting east-west traffic, you can also inspect north-south traffic, such as traffic egressing to the internet. Another advantage is that it offers a clean separation of duties. Application developers tie security groups and NSGs to the lifecycle of their application workloads, and network or security teams handle layer 4 firewalls in the transit layer. This feature gives you the flexibility to create rules that allow or deny CIDRs, and also bundle CIDRs together into tags to further simplify creation of rules. With single AZHA enabled, the controller monitors the health of the gateway and restarts it if it becomes unreachable. The centralized stateful firewall feature has several operational benefits. The controller manages all the route tables and firewall rules. You don't need any additional constructs such as load balancers. And finally, the interface for creating rules is identical across all clouds, making it ideal for a multi-cloud environment. Let's see how this architecture builds out in various clouds. Starting with AWS on the left, you have application workloads in the spoke VPCs in the application layer. You create firewall rules on the transit gateway from the Aviatrix controller. When you're growing to other clouds, such as Azure, all firewall rules will still be managed by the Aviatrix controller. It really doesn't matter which cloud you're in or how many you have. The UI is all the same. Here, we're extending into GCP. It's the same repeatable architecture being managed from the Aviatrix controller. Next, let's discuss Aviatrix Transit FireNet solution with next-gen firewall insertion. Before we get into the solution, let's understand the problem statement. The business requirements may state that Layer 7 security is a must, or that it is required for security or compliance reasons. Or maybe there's a technical requirement to perform deep packet inspection on certain environments. Or maybe there's an inclination based on comfort level to use a certain firewall vendor in the cloud that was also used in on-prem. Now let's talk about the different traffic patterns that might require a next-gen firewall. There might be a need to inspect traffic for applications that need to cross boundaries of VPCs, VNets, or VCNs. For apps that require ingress access from the internet or egress access out to the internet, then you might need to inspect their traffic as well. Let's say you are connecting your on-prem data center to the cloud. Maybe you're consolidating certain on-prem functions, such as firewalls, and moving them to the cloud. The on-prem could also be remote sites, such as partners, where there is a lower trust level. That's another reason to inspect that traffic with a next-gen firewall. And finally, when traffic needs to cross region boundaries or cloud boundaries, you might want to have it inspected by a next-gen firewall. For all of these reasons and traffic patterns, you will need intelligent service insertion. Now let's talk about some of the challenges of service insertion in the cloud. In particular, let's take a look at it from the perspective of firewall vendors. Firewall vendors actually repackage their on-prem appliances into the cloud. The downside of this approach is that it doesn't address the networking challenges in the cloud. That means that they expect the customer to determine the routing and redirection of traffic to and from their firewalls, which is a very difficult thing to do properly. From the CSP's perspective, as we discussed previously, they lack enterprise-grade networking features that customers are used to in the on-prem world. They also expect the customer to own the routing piece, the service chaining with firewalls. Moreover, when using native CSP constructs, there are major challenges with lack of visibility and troubleshooting tools. So where does that leave you, the customer? You are responsible for figuring out the routing and the troubleshooting. In order to build an enterprise-grade design, there are many advanced components that need to be involved, such as load balancers, source NAT, and route tables. And each CSP has a different approach to handling these components. Even after handling all of that, you're left without visibility and troubleshooting tools. The solution is to use the Aviatrix Transit Firewall Network, also known as FireNet. The architecture is exactly the same with the transit spoke architecture of MCNA. What you see here are next-gen firewalls deployed in the transit layer. With FireNet, traffic is inspected in a deterministic, policy-driven manner. For example, if you wanted traffic entering or leaving spoke 1 and spoke 2 in the diagram to be inspected by the firewalls, you can state that in your inspection policy. In that case, traffic entering or leaving spoke 3 and spoke 4, which might be less important environments, will never be inspected by the firewalls. Firewalls are deployed with AZ level HA, and you can deploy up to 20 firewalls in a transit from the Aviatrix controller. All the routing, traffic steering, segmentation, and connection policies are handled by the Aviatrix controller. So, for example, if spoke 1 were line of business 1, spoke 2 were line of business 2, and so on, then they would be placed in separate network domains, and you would be able to enhance the security even further. Just because there are multiple layers of security, such as encryption as well as inspection with a next-gen firewall, doesn't mean you have to sacrifice visibility. Copilot will still be able to provide deep visibility and operational capabilities. The entire architecture repeats itself, whether it is within a region, across a region, or across clouds. You can insert any next-gen firewall you want. Aviatrix has deep API-level integrations with Palo Alto Networks, Checkpoint, and Fortinet. However, you can even bring your own firewall appliance or load balancer, such as an F5 appliance. The architecture for Transit FireNet is identical to the architecture for the stateful firewall feature on Aviatrix gateways that was shown earlier in this module. The difference between this diagram and that one is that instead of a layer 4 stateful firewall being used on Aviatrix transit gateways themselves, you are now using next-gen firewalls in the Transit VPC, Transit VNet, or Transit VCN. Let's take a closer look at the Aviatrix multi-cloud service chaining feature. In this diagram, we have a two-cloud environment, AWS on the left and Azure on the right. You can have east-west, egress, or ingress traffic patterns inspected by the architecture. You can bundle this with high-performance encryption, which is discussed in a separate section in this training. All firewalls are active-active across availability zones, and there is no requirement for enabling IPsec, BGP, or SourceNAT. Route management is completely handled by the Aviatrix controller. This includes firewall deployment and user-defined routes or UDRs and VPC route propagation. The controller also provides improved failure detection and failover by performing automated health checks of the firewalls. Certain applications require different hashing algorithms when integrating with load balancers. Specifically, some require 5-tuple hashes, others require 2-tuple hashes. The Aviatrix platform provides different traffic steering based on your application requirements. Bootstrapping support is also provided by the Aviatrix platform. You can take advantage of Bootstrap packages to deploy your firewalls in a zero-touch manner, which is desirable for day zero operations. Now let's talk about how Aviatrix provides threat intelligence security with a feature called Threat IQ with Threat Guard. Internet access is pervasive in the public cloud. With some CSPs, it is on by default by simply giving a public IP to a virtual machine. This introduces business risk for data exfiltration, such as botnets, compromised hosts, crypto mining, Tor traffic, and distributed denial of service attacks. Oftentimes, enterprises will invest in third-party services like honeypots that offer threat intelligence. But those are inefficient and ineffective because experienced hackers can distinguish them from real production systems and either avoid them or take them down before unleashing their attack. Moreover, honeypots require specialized skills to implement and operate. Aviatrix gives control back to enterprises with a solution called Threat IQ. This feature allows you to identify, alert, and remediate potential threats to known malicious destinations. Threat IQ takes advantage of the distributed data plane that you as a customer own when you use Aviatrix. The distributed data plane refers to the Aviatrix gateways at every hop in your multi-cloud network. Threat IQ will identify and alert you on data exfiltration, as well as the hosts that are compromised by bad actors. Because it is using the distributed data plane, there is no performance impact whatsoever to the gateways in your network. Threat IQ is a complementary solution with Copilot that works with all clouds. Let's go over how Threat IQ and Threat Guard actually work. Aviatrix gateways across a multi-cloud environment send real-time NetFlow data to Copilot. Copilot analyzes the data on all public destinations against a well-known threat database. Within Copilot, Threat IQ provides extreme visibility of the impacted communication flow. Threat IQ also alerts you on any potential threats in your environment. Now, having this knowledge is one thing, acting upon it is another. Remediation is handled by Threat Guard. Copilot informs the Aviatrix controller to push stateful firewall policies to all the Aviatrix gateways in the data path. Firewall policies automatically get updated with the current status of the threat. Now let's talk about anomaly detection with network behavior analytics. Traditional signature-based solutions are not cloud-aware. They generally feature only a single point of inspection, and they function with a legacy operational model. This leaves the enterprise vulnerable to unacceptable business risks, including data loss, data exfiltration, and resource hijacking, which results in potentially devastating financial impact, not to mention loss of customer trust and significantly reduced agility. Network Behavior Analytics, or NBA, is a capability of Copilot that uses your workload and traffic characteristics as a behavioral baseline to identify and alert on abnormalities in your network. In other words, it is fingerprinting your environment and it continually adjusts through ongoing analysis. This provides a new approach to complement existing signature-based threat defenses. Through ongoing data collection, Copilot is able to alert when application and network behavior break this pattern quickly, identifying areas for security personnel to investigate. NBA can significantly reduce the time taken to resolve security breaches from occurring. This lowers the business risk of the financial implications of security incidents, which on average is more than $4 million for U.S. enterprises. Moreover, Enterprises are challenged with hiring and retaining professionals trained in cloud security. By implementing NBA, companies can uplevel and upskill their current talent, and so it allows for a leaner operation.